Hello and welcome to the ordinary least squares video tutorial for ECON 4650. The objectives of this video tutorial are that we'll be able to manually calculate estimated regression coefficients using the OLS estimator. We're going to explore data through summaries and plots. We're going to perform univariate and multivariate linear regressions in R. We're going to interpret those regression outputs and summaries. We're going to be able to manually calculate total sum of squared, explain sum of squared, residual sum of squares, and R squared, adjusted R squared, and correlation coefficient R. And we're going to be able to extract data from model summaries. So for the ordinary least squares module, the first thing we're going to be doing is the manual calculation of estimated regression coefficients. And so what we're going to want to do is read a CSV file into R as a data frame, just like we did in the last video. And so the file is finade2.csv, which is available on the course module on Canvas. And I'm going to change my current working directory to get to where that is. So I'm going to say set wd and change that. And I'm going to try and find the file there. And finade2.csv is right there, so that's great. So I'm going to go ahead and read it in. So we're going to say read.csv. Well, we're going to name it my data. And we're going to read that in as read.csv. And in quotation marks in all caps, finade2.csv. Header equal to true. This data does have a header. And we're going to say strings as factors equal to false. This will help us with the analysis that we're going to be doing. And we can get a look at that data that we just brought in with the head command, head my data. So we see here we've got the financial aid data, parent financial contribution data, high school rank by GPA, and we've got a dummy variable there for male or not male. So the first thing we're going to do is attach our data so we can so that we can easily manipulate it. So we're going to say attach my data, and so what we're going to do is we're going to calculate manually estimated coefficients using the OLS estimator, and this is done in the first section of this chapter of the text. So for ease of understanding, we're going to take our dependent or left-hand side variable finade and set it as y. And we're going to set our right-hand side variable HS rank as x. Excellent. And now we need to tell R what to use for y bar and x bar, which is easily done with the mean command. So we're going to say y bar is equal to mean of y, and x bar is equal to the mean of x. And next we need to create vectors for the quantity y minus y bar and the quantity x minus x bar. We're going to call those y diff and x diff respectively. So we're going to say y diff is equal to y minus y bar, and x diff is equal to x minus x bar. And to get an idea for what we're creating here, let's combine the vectors we're creating into a table using the column bind or cbind command. And then we're going to use the head command to view it. So we're going to say this is our table, and cbind y, x, y diff, and x diff. With the cbind command, you can write the columns in order that you want them to appear there. And then if we say head of table, then you'll see that this looks pretty similar to the first few columns of Table 1 on page 39 of the text. So just giving you an idea here as we move along and we do intermediate calculations, you can add these vectors to this table if you want. It's not required, but I was just trying to give you an idea of what this looked like as we move along. So next we need to calculate the quantity x minus x bar squared and name it x diff SQ for square. So we're going to say x diff SQ, and it's going to be equal to quantity x diff raised to the second power. And we also need to calculate the quantity x minus x bar times y times quantity y minus y bar, which we're going to call product. So product is equal to x diff times y diff. And now we're ready to calculate beta hat 1, which we can do using the sum command in R, and we're going to assign the name beta hat 1 to that output. So beta hat 1 is equal to the sum of that product we just created divided by the sum of that vector x diff SQ. And we can look at that. 64.7 approximately. And now that we've got beta hat 1, we can calculate beta hat 0, the intercept coefficient. So we can say beta hat 0, and that's going to be y bar minus beta hat 1 times x bar. And looking at that, it's about 6,396 or 6,370 with rounding. So let's check that these estimators look right. So we're going to determine the estimated regression coefficients with OLS automatically through R using the LM function. So LM is a cool function because it allows us to write out the equation similar to how we'd write it on paper, with the left-hand side variable on the left side, then a tilde, and the right-hand side variable after that. And we're going to want to name our results so we can save them. So we're going to save them in a new arbitrary variable called LM1. So we're going to say LM1 is LM function of y and tilde x. And if we take a look at LM1, we'll see here that it's got the function call. So this is what we told R to take in and calculate for the formula equation. And we can see our coefficients here, which we just estimated manually. So beta hat 0 matches up with what we have, and so does beta hat 1, the estimated coefficient for the x independent variable. So having computed the estimated regression coefficients in OLS or in R with OLS manually, and having checked it with LM, now we can move on to a more typical procedure for estimating regression coefficients with R, which is going to involve essentially looking at the data, examining it first, and then running the regression and looking at the results. So OLS estimation with R functions. So we're going to explore the data first with the summary command and then making some graphs. So if we look at our left-hand side variable and we say summary of FinAid, we can see some basic information there, and we're just kind of looking at the structure of how the data is laid out. Is it approximately symmetrical or not? What's the mean like? And it's often helpful to explore this variable visually, so we can use the histogram, which is something that we did in the last section. So you can say hist of FinAid, and it'll blow out a giant graph if you're on Mac. If you're on Windows, it should size it automatically for you. So we'll size that up pretty well and move that over here. And next we can refine the histogram by adding a smooth curve called a kernel density curve. This is going to add some information to our exploration. So you can think of this as an approximation to the actual probability density function. So to do this, you're going to want to write hist finaid prob equal to true, and you're going to want to write lines density of finaid. And we can see over here we've got that kernel density function. So what the kernel density function does is it gives us a little more information than the histogram, in the sense that it takes each individual data point for finaid and assigns it this kernel, or this small Gaussian distribution, and then it adds them up. And so we have a little more accuracy for the shape of our sample data here. And we gain some information because it's showing you a little more than what the histogram's doing. So when you're talking about the kernel density function, it's typically going to dictate the width of those little kernels that it stacks up, which we call bandwidth, by the standard deviation of the distribution that it's using. So in this case, the Gaussian distribution. And so basically it's going to put those side by side and then stack them up and just give you some information on how that probability density function looks. So now we can do the same analysis with our independent variable HS rank. So we're going to say summary of HS rank, and looking at the data again there, it looks like it is a little skewed toward the right, so we've got a little more data on people with higher high school rank GPAs. And we can go ahead and put the histogram with the probability density function on there as well. So we're going to say hist of HS rank probability equals true, and then lines density HS rank. And once again, you've got that going on. And if the explanation of the kernel density function wasn't very clear, that's okay. It's not critical that we understand it at this point, but just know that it's that it's going to give you a little more information than the histogram because of the way that it spaces out the data, and it's just going to just be a more detailed look there. So now we're prepared to run our regression. So once again, we're going to utilize LM, and we're going to use a new function AB line, which is going to use the estimators from the regression line to draw a line on the plot. So as before, we're going to want to save our results. So we're going to say my model, and we're going to say LM finaid and HS rank. And then we're going to type my model. Oops, we're actually going to want to do summary of my model. It's going to give us a little more information. So the summary screen, there's a lot of information on here. Once again, we've got the call, and you've got some information on the residuals there. But we're going to look in this course module, we're going to be looking at the coefficients and at the r squared and the adjusted r squared. So here we've got our coefficients, which look the same as the ones that we calculated before, which we would expect because before we had just renamed these same variables. So we've got a positive coefficient for HS rank with regards to financial aid, which makes sense. So the higher your high school rank GPA by 1 unit, your financial aid award is going to go up by a little over $64. And the beta hat 0 intercept here. And we've got an r squared value kind of describing, as we learned in the text, the fit of the regression to the data. And we've got adjusted r squared, which is going to come into play as we start adding variables, and we want to see how r squared is changing not only with the added variables but with the reduced numbers of degrees of freedom. And you can basically ignore the significance codes here. We're going to get into that next section. And so now we're going to insert a linear regression line into a plot of the data. So by convention, we put our independent variable on the x-axis and the dependent variable on the y-axis. And with plot, this means naming the independent variable as the first argument and the dependent variable as the second. So the third argument is going to be using the AB line command to insert the regression line that we established. So that's a lot of talk, so let's see how it looks. So we're going to say plot of HS rank, and then FinAid, and AB line of my model. And I typed AB line wrong, and that happens. Let's try that. Excellent. So what AB line did is it took 2 points. You can think of it as taking points A and B, and the 2 points it took were the intercept estimate of the coefficient there, and it took the HS rank estimate and built a second point based off of that, and it plotted it here as a straight line. So you can see that it's at least fitting the trend of the data. We know from our R-squared value it's not fitting the data very well. R-squared is pretty low, but anyway, that is the basics of what we're trying to do here. So now we can move along to the multivariate regression model. And the OLS estimation of multivariate models is identical in general approach to the OLS estimation of models with just one independent variable. And we're going to demonstrate multivariate regression, we're going to extend our initial model twice. So the first extension, we're going to add the parent variable as an independent variable, and the second, we're going to add male, which is a dummy variable. So as we're adding new variables, we need to continue with our data exploration and just continue trying to understand the relationships between these dependent and independent variables. So let's call in a summary of parent, and that's there. So we can see that the mean is considerably higher than the median, which we'll see is probably due to an outlier on the high side. You can see that the third quantile is only just above 17,000, whereas the max is 64,300. So let's plot this and get a better idea for what's going on here. So hist of parent, probability equal to true, and make sure you capitalize true. And then we're going to do we're going to put the density line in there. So lines density of parent. And we can see there we do have an outlier on the high side, and otherwise most of the data seems to be grouped down here. And then we can plot the relationship of parent with FinAid. So let's do a plot parent FinAid. And so we see, as we would expect, there's generally a negative relationship between the amount of financial aid rewarded as the amount that parents can contribute to education increases. So nothing mind-blowing there, but we're just kind of looking at that data. So having done this initial data exploration, we're going to run and interpret a multivariate regression. So in R, this is pretty simple. You just add the new independent variable to the right-hand side of the model specification. So if you say my model, and you say LM, and again we've got FinAid on the left, and parent, and then you just add that second independent variable, so HS rank. And you're going to do the summary of my model. We're just writing over our old model there. And I forgot to write my, that's okay. So looking at summary of my model, we see a few things here. We've got our intercept estimate, beta hat 0, and we've got our parent estimate of the coefficient there, which is negative, as we would expect, and the HS rank there. And we see that the model seems to be fitting the data at least better. It's got a multiple r squared of 0.7441, and we've got an adjusted r squared here, which we're going to pay attention to as we add another variable and see if that went up or down, as that's going to tell us more because it's accounting for those reduction, or for that reduction in the degrees of freedom. Now we can go ahead and pull up the coefficients on their own, so that we can kind of investigate the relationships between these independent variables graphically by themselves against financial aid. So if you say coef of my model, it'll pull up the three coefficients that we have there. And I think it's going to be helpful to visualize if we create some plots of these relationships. These are going to be really similar to the plots on page 44 of the text, which illustrate these same points. So let's look at the impact or the relationship of parents' ability to contribute to the financial aid award. So we can ask R the following. Let's have it plot parent, fin aid, and then AB line, and we're going to tell AB line to perform the command that we just did. So AB line is going to grab the coefficient from my model, and which coefficient? We're going to tell it to grab the first one. And we also want it to grab the second coefficient because that's the one that R knows as the parent coefficient. So we're going to say coef of my model and the second one. And so here, though the scale will be different than what's in the book, you can simply see that you do have that negative relationship, and you can see that it's pretty apparent. And once again, we just practice using AB line, telling it specifically which points to use to plot that line. So similarly, we can create a graph for financial aid and high school GPA rank if we say plot HS rank, fin aid, AB line, coef of my model. Once again, we want that first one, that intercept, and coef of my model and the third one. And so that's going to give us the relationship between HS rank and fin aid, which is positive as we would expect. And so finally, we're going to introduce the idea of a dummy variable and include them in the regression. And before we do this, let's remember what our adjusted R squared was before we add this variable. So the adjusted R squared of our old regression was 0.733. And so the best way to look at a dummy variable, since it's basically categorical, like 0 or 1, male or not male, is going to be to use the table function and look at the data. So let's say table of male. Don't get this confused with the object we named table. This is a different thing. This is a function called create a table out of this data. So table of male says we have 23 data points that are male, or 1, and 27 data points that are not male. You can interpret that however you'd like. The text seems to interpret it as kind of a gender binary, and that's what we're going to use for this example. So now we're ready to include that as an independent variable. So let's say my model, once again, my model is our workhorse here, LM fin aid tilde parent plus HS rank plus male, and we're going to do summary of my model. Before we do anything else, let's look at the adjusted R squared. It went up. We added a variable, so we know, or we would expect that the normal R squared would go up, but the adjusted R squared went up, which is a good thing. Try and be sure that you can understand why that is significant. And the answer to that is in the text. So this is great, and it added estimate. So it does seem like male has a very small estimated coefficient that is negative, such that if you are male, it seems like that would give you a slightly lower financial aid reward. But we need to judge that in the context of the significance of the estimate over here, which we'll get into in the next module. And good data hygiene is going to require that we detach our data set when we are finished with it. So let's say detach my data. So now we're ready to talk about total explained and residual sum of squares. So we know that the square difference of y around its mean is used to measure how much of the variation of the dependent variable is explained by the estimated regression equation. This is called the total sum of squares. And we know that total sum of squares has two components. It's got the variation that can be explained by the regression and variation that cannot. Right? So explained sum of squares measures the amount of the squared deviation of y from its means that is explained by the regression, and the residual sum of squares is the part of the total sum of squares that is unexplained by the estimated equation. And basically, the smaller RSS is to TSS, the better the estimated regression line is going to fit the data. So that's a lot of talk. So let's start plugging it into R and figure out what's going on. So to apply this, we need to return to the manual calculation of estimated coefficients with OLS that we did before. So to calculate TSS, we need the estimated y hats. So to calculate this, we have, I guess a better way to say it is the fitted y hats, right? So these are the y's. These are the y value that the model predicts, and then we can compare those to the actual y value. So to get the predicted y hats, we are going to have R use the estimated equation of the model, like what's on page 34 of the book. So we're going to say y hat is equal to beta hat 0 plus beta hat 1 times x. And this is going to give us a bunch of estimated y's, right? So y hat, great, look at all that. So now that we have the y hats in our data, we can calculate the residuals. This is one way to do it, where the residual is equal to the actual y value minus the predicted y value for each data point. So we're going to say resid for residuals is equal to y minus y hat. And we can look at resid. We've got a bunch of residuals there. And now you can calculate the explained sum of squares as ESS is equivalent to the sum of that quantity, that sum of y hat minus the mean y bar quantity squared. And then we've got the ESS, excellent. And we can also calculate the RSS, the residual sum of squares, by doing the sum of the squared residuals, so resid caret squared. And that is a fairly large number. And finally, the total sum of squares is going to be equal to the sum of y minus y bar, or the mean quantity squared. And we know that the TSS, or total sum of squares, should be equal to the explained sum of squares plus residual sum of squares. So let's check that out right now. So TSS, and then if we look at ESS plus RSS, it is the same number, so that's excellent. Our math is good. And now we can move along to calculating r squared. So we know that r squared is equivalent to the explained sum of squares over the total sum of squares, which is the same as 1 minus residual sum of squares over total sum of squares. And again, r squared is just measuring the percent of variation of y around y bar. So let's do r squared. Let's call it r2. And we're going to do explain sum of squares over total sum of squares. And look at that. So that gives us a number. And to check this, let's grab the r squared value from the LM model that we executed in the first part of this module by telling the summary function to grab it for us specifically. So this is great. So we're going to say summary LM1, and then we're going to put a dollar sign, and the dollar sign is going to tell R, okay, you're looking in the function that we just did, which is the summary of L1, and after the dollar sign is going to tell it specifically what we are looking for, so r dot squared. Excellent. So it just pulled the r squared data out of that summary, and we see that it matches up with the one that we calculated, which is great. And again, as you may have noticed, the r squared is rather low. This was from our first estimated regression line, and it's not fitting the sample data very well. There's also an easy way to pull up the correlation coefficient in R. So you can say COR of y and x, and that'll give you that right there. And next we can go ahead and calculate the adjusted r square, which is going to again measure the percentage of the variation of y around its mean that is explained by the regression equation but adjusted for degrees of freedom, which again is really important. So we're going to calculate adjusted r squared, also known as r bar squared, from our last model specification, the one we just did called my model. So the first step is we're going to extract the residuals from R. This is an easier way of getting residuals than the way that we just did it, which was basically calculating them manually. So we're going to say resids, and we're going to say my model, and we're going to put a dollar sign and tell R specifically what we want to pull out of my model, residuals. And now we can square them and sum them up and get the sum of the squared residuals. We're going to call it RSQ, just for shorthand. Sum of resids hat 2. You may notice that sometimes I just put the caret right after the vector name, and sometimes I put them in parentheses. You can do it either way. R can figure it out. Just be careful when you get into complex equations that you don't get the caret after the wrong set of parentheses. So there's RSQ. And notice that the total sum of squares that we calculated previously, even though it's from a different estimated equation, it was still from the same set of sample data y's and their mean, so we can still use them, and it's still relevant to this calculation. So knowing that, we can calculate adjusted r squared. We'll call it r bar, and it's going to be 1 minus RSQ divided by 46, which is going to be equivalent to basically the number of our observations minus the number of coefficients, including the estimator, so 50 minus 4, and then we're going to divide that by the total sum of squared, divided by 49. I need to put a parenthesis in here. Simply the total number of observations minus 1, or n minus 1. And then if we execute that command and pull up R bar, we see that we get the adjusted R squared as 0.7493 approximately. And again, we can compare that to the calculated adjusted R squared from the My Model summary, the same way we've been doing. If we say summary of My Model with a dollar sign and tell it what we're going to pull out, in this case it's adjust adj.r.squared, and we see that our numbers match up and the calculation was correct. Thank you, and that is the conclusion of this video tutorial, and assignment 2 is available in Canvas in the OLS module.